Now, I will define this class of problems NP. This is also going to be class of all decision problems. But I will write this informally again. Okay, so this is a lots of some not so clear terms here. So, verified certificate. So, these are problems. Okay, so first of all, NP does not stand for not polynomial time. Okay, we do not know that yet. So, what does NP stand for? Non-deterministic polynomial time. So, if you are seen an automata course, you would have seen non-deterministic finite automata, non-deterministic push down automata, non-deterministic Turing machines. It is related to that non-deterministic Turing machine. So, if you want a formal definition, it is a set of problems for which there is a non-deterministic polynomial time algorithm that will solve the problem. Okay. To translate it in the language we are used to, it is a set of all decision problems. Decision problem means the answer is always yes or no, for which the S, if somebody has to verify the S answer, there is a way to verify it in polynomial time if given a certificate, given a proof of the S answer, one can verify in polynomial time. Okay, let us see some examples. So, this is not a again, if you have used non-determinism Turing machines, then it is very easy, because there is a guess, there is some path in the Turing machine which will lead to an accepting state given if the answer is yes. Okay. So, that path is actually the certificate. But let us see some examples and you will get the idea. So, suppose let us first of all, let us make this clear. P, the whole class, is contained in NP. Why is this? That I do not even need a certificate. If the problem is solvable in polynomial time, that algorithm itself is a certificate. So, I run that algorithm and I get the answer, and that is my verification. So, there is no, I do not need an extra certificate. So, if a problem is solvable in polynomial time, it also belongs to this class NP. So, NP is a bigger class, we think, and I will explain why I say we think. Okay. So, let us look at an example. So, suppose I give you a 100-digit number and I want you to check whether it is composite. Okay. 100-digit number, I want you to check, tell me, convince me that it is a composite number. Okay. How will you convince me that this number, 100-digit number, you spent 3 years trying to check that? I am not worried about how much time you checked, and you found out that answer is yes. Can you give me a certificate which I can verify easily? That is it. You just say 2483 divides this number. 2483 is a divisor of this 100-digit number. Okay. I do not know how you found out, you spent a lot of time, because that is, we are not talking about P, right. The time to solve that may take a long time, we do not know that, but you can give me a certificate which is a divisor, which I with my limited time can verify. What is my verification algorithm? I will divide, which I can do, right. So, I take your number and you tell me this is a divisor, I will divide it and verify that, right. So, compositeness, is the number composite, is actually in the class NP. Okay. Let us give another example. So, I give you a graph and I want to check whether it is Hamiltonian. Does it have a Hamiltonian cycle, right? What would be the certificate you will give me to convince me? Right? This is a very complex 100,000 vertex graph, right? I give you and say, okay, is this Hamiltonian? I don't, because I told you last time that we don't have an efficient algorithm to test that. So, you can't run an efficient algorithm and find out and tell me that, right? Then that algorithm would be a certificate for both of us. We don't have an algorithm, but how will you convince me that yes, this graph has a Hamiltonian cycle? So, you just give me a Hamiltonian cycle. What is a Hamiltonian cycle? You give me a permutation of the vertex set and you say, here is a cycle, go from 1 to 7083 to 42 to 11 to 81 and so on and so forth. And what is my verification algorithm? I will just go to my adjacency matrix and see that every adjacent thing which you have mentioned is actually an edge and that it covers all the vertices, right. So, here that is a decision problem. Is the graph Hamiltonian? Is the decision problem for which the S answer can be verified in polynomial time with the polynomial size certificate, right. So, let us write this. So, compositeness is the problem of whether it is in composite, Hamiltonicity so I mentioned about this prime. Is the number prime? It was a long standing open problem to come up with a polynomial time algorithm for this. Remember, here polynomial time means polynomial in which is what? Log n. I want a log power 10n or something kind of an algorithm, right. There is a long standing open problem. Even if you see Carmen's book, it will have some probabilistic polynomial time algorithm, but this problem was solved and it is a significant Indian contribution here. This is by Manindra Agarwal at IIT Kanpur and couple of his students. I forget, some 2004, okay. And the paper is titled Primes is in P. That this problem, given a number, is it prime, has a polynomial time algorithm, and polynomial here means polynomial in log n, right? And so this uses interesting properties of number theory, algebra, analytic number theory and so on. Or these two students were BTech students at that time. Now, since you can test whether a number is prime in polynomial time, in fact, compositeness is also in polynomial time, right? Why? If it is not prime, it is prime, right. So, here is a interesting observation. If L is in P, then L bar is also in P, right. In the language theoretic sense, that if I want to know whether a graph is Eulerian, if I have a polynomial time algorithm, and if I want to know the graph is not Eulerian, that also is a polynomial time algorithm, because you run that algorithm, if it says no, you know it is not Eulerian. So, this is true for polynomial time algorithm, okay, good. So, because of that reason, compositeness is not just in NP, also in P, but anything in P is in NP anyway. So, good. So, now so the big open problem is the converse true, right? Is NP contained in P? Right, look at this picture. Every problem in P is in NP. So, roughly the way to think about it is P is all problems which you can solve in polynomial time, and NP is set of all problems which you can verify in polynomial time, right. So, P is basically a student's job and NP is a teacher's job, right. Okay. So, your job, so the question is my job easier than yours? And in principle, it looks like that verification should be easier than actually solving it. So, most people believe that this containment is not true, right. The conjecture is yeah. So, NP, there are problems in NP which are not in P. Right. But wait, I already told you this, right. Hamiltonicity problem is the graph Hamiltonian, has a easy verification algorithm and it does not have a polynomial time algorithm. So, is not that an example to prove that you have a problem in NP which is not in P? So, why is this a conjecture then?
You can't prove that there exists no polynomial.
Very good. We do not know that there is no polynomial time algorithm, right. So, all I said about Hamiltonicity is that so far we do not have a polynomial time algorithm. That does not necessarily mean that it is not in P. So, that is a big open problem. Can you design a polynomial time algorithm for test whether a graph is Hamiltonian is one of the many problems for which we do not have a polynomial time algorithm, but we do not know that it is not in P as well. So, that is why this is a conjecture. Okay. But somehow these problems are related, we saw, right, that minimum vertex cover, max click, max independent set, they are all related. They do not have a polynomial time algorithm, but if you say that max click is here is not in P, then so is max independent set, so is min vertex cover. If any one of them belong to P, all of them belong to P. Is there a notion that captures it? And yes, that is this. Let us talk about this reduction, right. So, I am going to introduce this notion of NP completeness. We have defined the class P, we have defined the class NP. Now, I want to get to defining this notion of NP completeness, right. Reductions is something we have seen. We have reduced collection of max independent max edge disjoint paths to network flows. We have reduced min vertex cover to max independent set. We have reduced max independent set to max click. Let me formally define this, right. So, you have a problem or a language reduces in polynomial time to L2 means what? If there exists a function of polynomial time algorithm so let us call this algorithm F that converts any input x for L1 to f of x for L2 such that x is in L1 if and only if f of x is in L2. Okay, so didn't say things precisely. So, here is my remember the way I defined what is a problem is in terms of this language, right. So, here is set of all instances for my problem. So, let us maybe call it P1. And L1 is S of P1 and L2 is okay. So, I have two problems P1 and P2. So, think of this as vertex cover and independent set or max edge disjoint paths and network flows. So, and we are talking about decision problems. So, we can reduce this problem to this P1 to P2 if for any input. So, there is some algorithm, polynomial time algorithm, which converts any input x here and it translates it to f of x here, such that the s instances go to s and no should go to no. Okay. So, anything here, these are all the s should go to here and anything outside goes outside. Right. This is just formalizing whatever we talked about. So, how did we reduce click to independent set? So in this case I am going to write this notation as P1 reduces to P2, which means that you can use an algorithm for P2 to solve a P1, right. How did we reduce click to independent set? What is the function f? What did it do? Right. What does the function do? So, both have set of all graphs as the instances, right. I want to reduce from click to independent set. So, what it should do is to take an instance here and convert it into an instance of this, such that an s would correspond to an s and no would correspond to a no. So, what was the function doing? It was just complementing the graph from click to vertex cover, right. When we went from here, we complemented it. So, that is all the notion of reduction is. We have seen it in multiple examples: click reducing to maximum independent set, collection of max disjoint, edge disjoint paths reducing to network flows, and so on and so forth. Only the thing is that here we insist that this reduction takes polynomial time, right. Why? Because a corollary of this is that if P1 reduces to P2 and P2 has a polynomial time algorithm, then P1 has a polynomial time algorithm. This is why the reduction is defined this way, because the time for P1, what is the polynomial time algorithm for P1? So, P1, I take my input for P1 and then, so because P1 reduces to P2, there is some function which will translate this input, apply that function, that polynomial time algorithm, which will take the input for P1, translate it to an input for P2, then run the algorithm. So, we made two assumptions: P1 reduces to P2 and P2 has a polynomial time algorithm. So, run the polynomial time algorithm for P2. From the answer, you recover the answer for P1, and that would constitute a polynomial time algorithm for P1, and that algorithm's running time would be whatever time it takes for your reduction plus whatever time it takes for P2. Okay. So, now we want to define some notion of hard problems in NP. Okay. So, here is this picture where P is sitting inside NP, and I want to somehow capture some problems here which are hard in NP, and these are problems for which every problem in NP reduces to this. So, let us define this class NP hard. These are decision problems again, because everything in actually these need not be. Problems to which okay, maybe you can stick to decision problem. Every problem in NP reduces to. So, what is an NP hard problem? So, here is a problem pi. It is an NP hard problem means that every problem in NP reduces to this problem. because I already defined you what reduces to mean, right. You take any problem in NP, there is an algorithm which will translate the input there to an input of this problem. This is somehow capturing every problem in NP. In that sense, it's a hard problem. Every problem in NP, you take that input, there is an algorithm which will convert it to this, such that S instances go to S instances, no instances go to no instances. Take another problem that can also be reduced. Every problem in NP can be reduced to this problem. Okay. Now, first question you should ask is there such a problem at all, right? It's okay to have a nice definition, but the set is empty, it does not mean anything, right. We will come back to that question, but let me capture a nice corollary here. If pi is NP hard and is in P, then all problems in NP are in P. Very good, right? We have solved that conjecture, right? That conjecture, whether this containment is strict or is this containment true, is an open problem. And way to show this open problem, to solve the open problem in one way, is to say that pick an NP hard problem and give a polynomial time algorithm, right? Because of this corollary, if pi is NP hard, every problem in NP reduces to this, but if somebody reduces to this problem and this has a polynomial time algorithm, that has a polynomial time algorithm. That is what this corollary said. So, every problem in now NP will have a polynomial time algorithm. Okay. If there is such a problem at all, right, we haven't still shown that there is such a hard problem. So, the conversion is the same, G goes to G, that is the algorithm. Okay. And so, there is more work happening at the output level. So, the point is that we use a polynomial time algorithm for this problem, we use it and we may do some modifications, whatever we do, to solve the original problem. Okay, so, that is what it is. Okay, so, now back to his question, how do we show that every problem in NP reduces to a particular problem? That looks like, because there are infinite number of problems, that is number one. Number two, is there some problem at all which is NP hard? So, I am not going to, I will answer one question, one of the two questions. So, there is a famous theorem by Cook and Levin in 1971, who showed that there is one problem which is NP hard. Okay. And that problem is a more general version than this, but let me simplify it. I will tell you how he showed it. So, what is the satisfiability problem? So, let us get to that problem, right. So, satisfiability problem is input is a formula, a Boolean formula, CNF formula. Okay, this is not exactly what Cook and Levin showed in that paper, but this is some simplification of what they showed that were obtained later. Boolean formula F, which is a conjunction of some clauses each Ci is okay, maybe there are some bars. So, this is just an example. And the question is, so it's a Boolean formula on m clauses and n variables. And the question is there a 0 1 assignment to the excise that satisfies all the clauses. Okay. So, now we are moving into a different domain, Boolean formulas. So, we have a formula which is a AND of a bunch of clauses, okay. AND is a conjunction of various clauses. What is a clause? It is a OR of some variables or their negations, okay. A clause. So, an example would be, so okay. So, it is something like this. So, it has 1, 2, 3, 4, 5, 6, 7 variables and 4 clauses. So, I have to write one more clause. So, it is a conjunction of 4 clauses and each clause is a collection of some R of some variables. Okay. And what is this is, so this is the input to the satisfiability problem, and the question is, can you set x 1, x 2 up to x 7 0 or 1 variables such that every clause is satisfied? When does a clause get satisfied? See, 1 gets satisfied if x 1 is 1 or x 7 is 1 or x 3 is 0. C 3 gets satisfied if x 1 is 0 or x 2 is 0 or x 6 is 1 or x 3 is 1, and so on and so forth. Okay. Now, the question is there a way to assign these variables zeros and ones such that simultaneously you can satisfy all the clauses? Is there an assignment here? Give me an assignment, 0 1 assignment for the variable that will satisfy all the clauses. X 1 is 1, x 2 is 1, okay. Any other variable can take anything else. So, x 1 is 1 would satisfy C 1, right. So, to satisfy this, any one of this is enough. X 1 is 1 or x 7 is 1 or x 3 is 0 is enough. So, x 1 will satisfy this, x 2 is equal to 1 would satisfy this, but x 1 is 1 will make this 0, will make this 0. So, you need something else to satisfy this, which is x 3, x 5 is 0 will make this 1, and x 4, x 6, x 7 whatever you like, does not matter. So, this is the problem. Given an input instance, can you design a general algorithm that will test whether the formula is satisfiable, right? Can you give an exponential algorithm for this problem? Some algorithm, a brute force algorithm, what will you do? Try every 0 1 combinations. How many are there? If there are n variables, 2 to the n combinations. For each combination, once you give me a combination, I can verify, right? Because I just have to run through the formula and check whether I just now did, right. I do not know how she came up with the assignment. Once she gave me the assignment, I verified that it is satisfiable. So, it shows a lot of things. First, the problem is in which class? NP, right, because the S answer has a certificate which can be verified in polynomial time, because you just give me an assignment as a certificate, I can verify, run through the formula, and it has an exponential time algorithm. And it is also one of those problems for which we do not have a polynomial time algorithm. Now, what Cook and Levin independently showed is that every problem in NP can be reduced to this problem, right. Now, his question is, how do you reduce every problem in NP, because there are infinite number of them? Well, use the definition of NP. What does, so you take any arbitrary problem in NP, use the formal definition of what does it mean by it's in NP. It is a non-deterministic polynomial time algorithm. For given any input x, there is a non-deterministic Turing machine, it will run in polynomial time and it will answer S answer, it can verify it, right. Write down that Turing machine. So, you are given that Turing machine and then what they did is converted the Turing machine computation into a big Boolean formula. Okay. So, the whole Turing machine so it takes some p n many steps, because polynomially means, let us say n cube many steps, right. All this is given because the problem is an NP. Okay. Now, you do not have to take a specific problem in NP like a vertex cover and so on, then you are not showing it for every problem in NP, but you use the formal definition of a problem in NP. And then what they did is to convert the Turing machine computation into a huge formula, and showed that this Turing machine on this input will say yes and answer in polynomial time with a certificate if and only if this formula. So, or this Turing machine will accept the input and say yes or no for your non-deterministic problem, right, NP problem, if and only if that this formula has a satisfying assignment. The satisfying assignment would be the computation path in the Turing machine. Okay. So, everything boils down to minutely describing the Turing machine as a Boolean formula, and that would give you they proved this problem. In fact, both, at least Cook, won Turing award for this paper, this work of NP completeness. So, we have so from Cook's theorem, which I have not described, but Karman has a version of it in big detail. Circuit satisfiability problem is NP hard, is what is described in Karman's book, and picks up an arbitrary problem in NP and gives a reduction in that book. So, we have shown existence of one problem which is NP hard, and because of this corollary, now we know that if satisfiability problem has a polynomial time algorithm, then every problem in NP will have a polynomial time algorithm. Okay. Since it is so powerful statement, which we do not believe, because we believe that verification and computation are inherently computationally different set of problems, we do not believe that satisfiability has a polynomial time algorithm. Okay. So, showing some problem as NP hard is an evidence that it probably does not have a polynomial time algorithm. Okay. So, now later in 1972, Richard Karp, who also won Turing award, showed a number of problems. Okay. So, I don't vertex cover, click, independent set, Hamiltonicity, dominating set, a whole bunch of them are NP hard. We know that these three will go together. If any one of them is NP hard, we know the other is NP hard, because of this polynomial reductions between them anyway. Now, how would you show that, right? How would you show that any of these problems are NP hard? Well, in the next 2 or 3 lectures, we are going to see a lot of examples of it. But notice that now I do not have to pick and start from scratch the way Cook did and say every problem in NP reduces to this problem. I do not have to show that. What do I show? Satisfiability reduces to this. Okay? Because Cook has done the hard work of reducing every problem to satisfiability. I will show that satisfiability reduces to my problem, and that means that if this has a polynomial time algorithm, SAT will have a polynomial time algorithm. If SAT has a polynomial time algorithm, every problem in NP has a polynomial time algorithm. So, because these reductions are transitive, because of this polynomial time computations, this requires some proof that the blow up, the input size blow up is again polynomially blown up, and so it is enough to show SAT reduces to your problem. You do not have to show SAT reduces to your problem. If you have shown vertex cover is NP hard, I can use vertex cover as a candidate problem to reduce to another problem. So, to show a problem, a decision problem NP hard, give a polytime reduction from a known NP hard problem. And finally, let me stop with this defining this set of class of problems is NP complete if it is an NP and NP hard. So, NP hardness is just to give you some leverage for problems which are not in NP also they can get reduced from every problem in NP. So, if the problem also belongs to NP, which is the case with SAT, which is the case with Hamiltonicity, then these problems are NP complete. Okay. So, with Cook's work and Karp's work, this whole industry of NP completeness opened up, and now there are about thousands of problems. And because of this corollary, which I have written at the bottom, we do not believe that NP hard problems have a polynomial time algorithm, because this seems like an unlikely thing to happen, and there are thousands of problems people are trying to design polynomial time algorithms, and so we believe that these problems are inherently hard. Remember, I said that at some point we need to think about this. We do not have a polynomial time algorithm. Is it because the problems are hard, or is it because we have not understood them enough to come up with a better algorithm? Showing a problem NP hard is an evidence to show that the problem is actually hard. Okay. It may still happen that they have a polynomial time algorithm and P and NP may collapse, but at least if you show some evidence that it is NP hard, you know that it is in a class of about thousands of similar problems. They all are difficult or all are easy. Okay. Okay, good. I'll stop here. In the next few lectures, we will see concrete examples of how do we do reductions to prove problems NP hard.